In March 2023, an attacker walked away with $197 million from Euler Finance, one of the most respected, most audited lending protocols in DeFi. There was no stolen key and no broken cryptography. The attacker simply found one function that forgot to ask a single question: are you still solvent? Today we take the whole thing apart, rebuild the exact bug in Foundry, run the attack ourselves, and then fix it with one line. Let's go. First, what Euler did. Like Aave or Compound, it's a lending market. You deposit collateral and you can borrow against it. The one rule that keeps the whole thing solvent is health. Your collateral, after a safety discount, must always be worth at least as much as your debt. If it isn't, if you go underwater, then anyone is allowed to liquidate you. They repay your debt, and in return they seize your collateral plus a bonus as a reward for keeping the protocol solvent. That liquidation bonus is normal, and it's exactly what the attacker turned into a weapon. Here's the whole attack in 4 steps. Step 1, the attacker leverages up, deposits and borrows right to the edge of healthy. Step 2, and this is the bug, Euler had a function called donated to reserves meant to let you gift some collateral to the protocol, but it gave away your collateral without rechecking your health afterward. So the attacker donates their own collateral and instantly becomes underwater on purpose, and nothing stops them. Step 3. A second account they control liquidates that position, seizing collateral plus the 20% bonus. And step 4, because the bonus is paid from the pool, they withdraw more than they ever put in. The pool is drained. Let's slow right down on that word, donate, because it's the strange part. Your collateral is the money you lock up to back your loan. As long as it's worth more than your debt, you're healthy. Now there are 2 ways to take collateral out of your account. The normal one is withdraw, the money comes back to your wallet, then the protocol checks that you stay healthy, so it stops you if withdrawing would leave your loan unbacked. Donate is different. Donate to reserves also removes collateral from your account, but instead of returning it to you, it gives it away into the protocol's own reserve fund. You never get it back. It was meant as a way to gift a little to the protocol, but the buggy version forgot the exact check that withdraw has. It never verified you were still healthy afterward. So you're allowed to throw away your own backing and leave your loan completely naked. So why on earth would an attacker give away their own money? Here's the trick, and it's the key to the whole hack. To keep everyone safe, the protocol pays a reward, a 20% bonus to anyone who liquidates a loan that's gone underwater. You repay the bad debt, you take the collateral plus a bonus as a thank you for keeping the system solvent. Normally that only happens when the market genuinely crashes, so it's fair. Think of a shop that pays a $20 finder's fee to anyone who clears out an abandoned locker. Now the donate bug lets you declare your own locker abandoned on purpose. Then a second wallet, which is also you, clears it and collects the fee. Since both sides are you, that bonus isn't a reward for helping anyone, it's just free money pulled straight out of the pool that belongs to the other depositors. Sabotage yourself, then rescue yourself for the reward. That's the entire con, and now you'll see it run. And this is the real attacker, on-chain, labeled right here on Etherscan, Euler Finance exploiter. The red banner says it plainly, involved in a flash loan exploit on Euler. They used a flash loan to get the capital, ran this exact self-liquidation trick, and drained $197 million. There is an unusual ending to this one. You can also see this address has since returned the exploited funds back to Euler, but the mechanism is what matters. So let's rebuild it and run it ourselves. We've rebuilt the mechanism as a tiny lending pool in Foundry, and we'll prove it in 3 acts, all as real tests you can run. Act 1, the honest case, a genuine fair liquidation works exactly as intended. Act 2, the attack. We self-sabotage and self-liquidate and walk away with more than we deposited. And Act 3, the fix. 1 line and the identical attack reverts. Let's open the code. Here is the vulnerable pool in VS Code. Most of it is a normal lending market. Deposit, borrow, and a health check that says collateral times the collateral factor must cover your debt. But look at this function, donate to reserves. It subtracts collateral from you and adds it to the protocol's reserves, and then that's it. It never rechecks your health. The line that should be here, require the caller is still healthy, is missing. That single missing check means you're allowed to make yourself insolvent on purpose. Watch what that enables. Act 1, the honest test. A user, Bob, deposits 1,000 and borrows 800, comfortably healthy. Then the market drops 20%, a real price move, and now Bob is genuinely underwater. So a liquidator steps in, repays part of Bob's debt, and seizes Bob's own collateral plus the 20% bonus. This is the system working as designed. Liquidation only triggers on a real honest insolvency, and the bonus comes out of the borrower's own collateral. Let's run it. And there it is. The test passes. Bob was fairly liquidated and ends up healthy again. The protocol stayed solvent. Everything's working exactly as it should. And to make it concrete, let's run that same step on a live chain and view it in an explorer. Here's that honest liquidation executed on a real local chain and opened in Otterscan, a block explorer, just like Etherscan, status, success, transaction action, liquidate, and look at tokens transferred, Bob's collateral moving to the liquidator plus the bonus. This is the intended behavior, and it only happened because Bob was genuinely underwater after a real price drop. Keep this picture in mind, because the attack will look almost identical, with none of the honesty. Act 2, the attack, and notice there is no market crash this time. The attacker deposits 1,000 and borrows 900 right at the edge of healthy. Then this one line they call donate to reserves and give away all their collateral. Because of the missing check, it does not revert. In a single move, they've made themselves deeply underwater. On demand, they move the borrowed funds to a second account, and that account, which they also control, liquidates them, seizing the collateral plus the bonus paid out of the pool. Then they withdraw. Let's see the damage. Look the numbers. The attacker started with 1,000 and ended with 1,060, a clean $60,000 profit in our scaled down model, and the pool lost exactly that, drained by 60. No price move, no flash of genius, just a self-sabotage plus a liquidation they controlled. Let's see the theft itself, on-chain. This is the attacker's final move on the Explorer, the withdraw, and it's marked success. Now look at tokens transferred, 960 of the pool's tokens flowing straight out to the attacker's second address. That's the drain on chain in plain sight, real value leaving the pool with no genuine insolvency behind it, only the self-sabotage from a moment ago. Same shape as the honest liquidation, but this time the victim was the protocol itself. Now imagine this at full scale with a flash loan repeated, and 60 becomes 197 million, so the fix. This is the entire fix, and it's one line. In the fixed pool, donate to reserves does the same thing, subtract collateral, add to reserves, but then it rechecks, require that the caller is still healthy. That's it. If donating would push you underwater, the whole transaction reverts. The rule is simple and it's the real lesson. After any action that changes an account's balances, you must re-verify the invariant that protects the system. Euler checked health almost everywhere. This one function was the exception. Let's confirm it kills the attack. Act 3 runs the exact same attack, deposit, borrow, then the malicious donate, but against the fixed pool. This time we expect that donate call to revert with unhealthy. If it does, the attacker can never reach the self-liquidation step and the pool is safe. It passes, which means the malicious donate reverted exactly as we wanted, and we can prove that on chain 2. Here's that exact same malicious donate but sent to the fixed pool on the Explorer. Status fail with revert message unhealthy. The transaction was mined and rejected by the contract itself. The attacker can't even take the first step, so the self-liquidation never happens and the $197 million drain becomes impossible. One require checked on chain and the whole attack is dead. So the lesson, and it's a big one, a protocol's core invariant here, every account must stay healthy, has to be rechecked after every single action that can change balances. One unchecked path is all it takes. Mostly safe is not safe. The liquidation bonus wasn't the bug, it's a good mechanism. The bug was that you could trigger it against yourself for free. And remember, Euler was heavily audited by top firms and this still slipped through. Audited does not mean immune, which is exactly why understanding these mechanisms matters. Quick recap, Euler let you deposit collateral and borrow as long as you stayed healthy. One function, donate to reserves, changed your balances but forgot to recheck that health. So an attacker made themselves underwater on purpose, had a second account liquidate them for the bonus and drained the pool $197 million. And the fix was a single require, recheck health after donating. We rebuilt every step in Foundry and ran it honest, attack and fixed. If real hacks taken apart and rebuilt on a real chain is your thing, that's this whole channel. These take real work to make. If it helped, the wallet's on screen and there's a Ko-fi link below. Every bit funds the next one. Thank you. One missing check, $197 million. That's the pattern behind almost every DeFi hack. A single assumption quietly broken in code that everyone trusted. We rebuild them here in Foundry so you can actually see how they work and how one line fixes them. If that's your thing, subscribe. There's a new one every day. Tell me which hack you want next in the comments and I'll see you there.